say that.
What was the last thing?
All right, let's get started. Welcome everybody to our monthly science education seminar. I just want to draw your attention that we have a seminar every second Thursday of the month. And if you're interested and do not want to miss any new upcoming seminars, please email Wendy. Her email is back of the board. She will put you in the mail list. Right, so today we have Amy Pallant. Amy is a Principal Investigator from Concord Consortium. She's directing several NSF-funded projects on Earth and environmental science, focusing on the modeling approach to learn geoscience and Earth science. And her curriculum has been used in all 50 states in the United States. So we are very excited to hear her wisdom.
Thank you. Thanks for having me. Oh, I do have a microphone. I'm like, wow, I can hear myself talk. So thanks for having me and for inviting me. My plan here is to talk about a project that started just about 2 years ago. So it's still new, but I'm super excited about it. So I thought, I talked to you about it. There's going to be a lot of like hand waving and because we haven't gotten to that solid final research that I can talk about the final stuff, but it's based on years of work that I've been doing at the Concord Consortium. I started at the Concord Consortium about 19 years ago. Concord Consortium actually was founded 25 years ago by Bob Tinker, and his vision for the Concord Consortium, just so that you understand, is to ignite improvements in education using technology. And so it's not just having a computer in front of you, but it's actually thinking about what's the best way that the computer can help in things that are not otherwise easily taught. And so in particular, I worked on the molecular workbench when I first got there, so things so small that you can't see it, so computers can help you visualize. But I'm a geologist by training and finally got funded to do geoscience education about 10 years ago. Things too large to bring into the classroom. And so that sort of informs why modeling makes a good tool. The project I'm going to be talking about is NSF funded. It's in partnership with Penn State University. The folks there were part of a math science partnership that looked at learning progressions in plate tectonics and teacher training around it. And so the combination of the expertise is really been excellent. But it does take a village to do the work that we do, and we have scientists, we have programmers, we've got education specialists and curriculum specialists and graduate students. And so this work, though I'm presenting it, is not just my work. As I'm going to try, the overview of my talk is I'll talk about earth science and earth science education, and many of you know about it, but I'm going to repeat what you already know anyhow because it helps me frame everything. And then I'll talk about the role of Earth systems models in transforming education, and I will demonstrate the models from the curriculum and this project. And then I'll talk some about scaffolding student learning, because models by themselves are lovely, but don't necessarily always take away what you hope the kids will take away from them. Throughout, because this is new, this is my first time talking about this project, if I'm not making sense, please ask questions. Informal, and I will be demonstrating models, so that I'll be fumbling around here also. So let me start with a context about geosciences and geoscience research. What is true is that I think geosciences are both extraordinarily accessible and yet infinitely complex, right? Everybody has in some way or another thought about the geosciences informally, right? You go on vacation, you see these incredible vistas. Driving down highways and you see these cross cuts. The weather, the hurricanes coming. I mean, people are talking about geosciences, but when they try to figure out what's gone on to cause what's happening or what they're seeing, that's where the story gets really complicated. And that's where the geoscientists are extraordinary, because they can think about things that take mind-boggling amounts of time and over large amounts of space. Middle school students and high school students, not so good at that yet. And plate tectonics in particular, I think is the modern organizing paradigm for all of geology. You can teach almost everything through plate tectonics. And understanding it as a dynamic system really helps you reason about it. And so, person can learn about where earthquakes are and volcanoes and mountains, and you can put that together and, understand plate tectonics. Or you can learn about plate tectonics as this dynamic system, so conversely, this is the causal mechanism, and then integrate why things on Earth are happening and where they're happening and how they've happened over time. And then you can look back over time and predict towards the future. So, I think my main goal is to think about plate tectonics as dynamic, right? This is, and Earth itself is dynamic. So traditionally, earth sciences have been kind of the orphan child left on the side, because about a little over 100 years ago, it was biology, chemistry, and physics, because you could do labs in a classroom. And you can't watch mountain building in a classroom. It just doesn't work that way. And that, I would argue, things are changing now, and computers are helping, and technology is helping, that it now can become an investigatory science like biology, chemistry, and physics. And you can do this, explore the world via data and observations and models. And luckily, the next generation science standards agrees with me, or I agree with them, not sure which. And here's an example of a middle school performance expectation for earth science, which is you can analyze and interpret data on the distribution of fossils and rocks, continental shapes, seafloor structures to provide evidence of past motions. But teaching in schools is still really static and very much focused on definitions. It's very much boundary oriented. This is what's happening at a convergent boundary. This is what's happening at a divergent boundary. And not integrating the causal mechanisms, and not integrating that if you know what's happening on one boundary, it might actually help you understand what's happening another boundary on that same plate, that there's more than one boundary on a plate, that the plate actually, there's things happening all around it, and that what happens over here can affect other plates, thus Earth systems, right? And so static, it's still taught definition. What's a asthenosphere? What's a lithosphere? What's a convergent boundary? And that's where the project that I got funded by the National Science Foundation called GEODE is trying to focus on Earth's system. It's a dynamic system, and plate tectonics as dynamic. That's the setup. And the goal is to transform, we hope, the way we teach and the way we learn about plate tectonics, because we have the option of using these models to start that as the fundamental paradigm, and then all the other things are sort of feeding into that. So the NGSS, I just said everything in geology can be taught from plate tectonics. So we had to sort of take a stab at what we're really going to try to cover. And here are from the NGSS the disciplinary core ideas that we're focused on. In particular, we are looking at the interactions at plate boundaries. That Earth system is a system and it's dynamic, and trying to look at what's the causal mechanism for the geological events and the landforms that they see on Earth now. So that's the main core concepts. but NGSS doesn't leave us with that. They have to do science practices and cross-cutting concepts. And for those of you who are just doing science, research, the education world is trying to put frameworks on science practices to help you think like a scientist. And so we focused, though we probably hit almost all of the practices and all of the cross-cutting concepts in some way, we foreground a few of them and really try to emphasize some of them. So not surprisingly, developing and using models. We do that because we think models can help represent and explain the phenomenon, and that students can then use the computer models to actually make sense and develop some understanding. But what you'll see also, and you'll see this a lot, is the other piece that I'll talk about a little bit more later is the real focus on evaluating the limitations and the precision of models, as well as other aspects of strengths and weaknesses. So in the constructing and explanation, we have kids do a lot of explaining. That they use the models as their primary evidence. And then they also need to, or at least we hope they can then identify the gaps and the strengths and weaknesses of the models and the data that they're using. So, curated curriculum, you present only what you think they should see, because it's like, here, we'll get our point across, right? Or we have, curated this model. You have to make choices in a model, right? A model is not the real world. And so, to help students identify the limitations of what they have, like, okay, you've given me only so much. Based on this, I can make an explanation, but there might be more that I need to know. So having them sort of meta-think about what they're doing is an important piece. And we really hone in on this, and I'll show you how we've developed this in our argumentation items, which helps them identify flaws in the science that they're presented with, if there is flaws, weaknesses, and flaws in their own arguments, so that they can understand that science is a process itself. So this is, different and hard for the science teachers that we've worked with, because they really want the kids to have the right answer. And sometimes, we're saying, there's actually more that can be learned. And I can tell you, when I first started doing this 10 years ago, they told me don't. And they, meaning my advisors and the NSF program officers, because they thought I was going to make science doubters, right? What? I'm uncertain about something. Scientists might be uncertain about something. And so they told me not to, because I was doing a climate change curriculum, so it's even more loaded. But it is proven to be actually a really useful tool in education. And then finally, the cross-cutting concept. Systems and system models. Again, not surprising that this is where we're focused. But the thing with cross-cutting concepts, which I have the most difficulty with in terms of the education, is it's supposed to cross beyond what you're doing, right? Is can they take what they've learned in your work and apply it, in other domains, even in the same domain in other units. But that doesn't mean we shouldn't be trying, because eventually we all can get there. And so, the idea is to help the students proceed through and start to make sense of, this is an important concept, you'll see this other places. And so, focusing on modeling and the use of modeling. I'm talking really fast. I tend to do that when I start a talk. Any questions so far about what I've presented? Any thoughts?
What's the grade level for this work?
So this work, we work with middle school and high school, where they do it in high school, or science, you tend to find life, earth, and physical science in middle school. Mm-hmm. Some places have earth science either in the 9th grade or as the capstone. Like Texas actually has it as a capstone course. So, we are ranging, sort of 6th grade to 12th grade in terms of the focus. That the 12th grader may not have had any more earth science than the 6th grader does, so it's not that hard. Anything else? All right, so taken as a whole, the way we try to approach the curriculum is to mimic the way geoscientists do their work. And, what geoscientists do is they're gathering evidence through observations. They can be using satellite, they can be doing core sampling, but they are doing observations and they're pulling it together and they're investigating causes that lie in the world around them and then use that phenomenon as insight into Earth's past and making predictions towards the future. So the focus of how we try to do the materials in the curriculum is the same idea and practices that we think research scientists do. They don't get out into the field with our curriculum. They could, but and I will say, as we get into the curriculum, it is our expectations that we have a thread and that teachers can add and supplement with other classroom work, but we do the foundations. So now getting into really why I came is because I want to show you my models. So models in education hold the potential, I think, for transforming plate tectonics education in particular. Partly it allows students to think holistically and to actually reason about mechanisms and interactions because they can observe both the data and gain insights into it, as well as emergent phenomenon. And so I'm going to be showing you two different models that I've developed with my team for the GEODE project. One which is called the Seismic Explorer, which is a data visualization tool. That model integrating earthquake, volcano, and plate motion data sets. So I'll show you what that looks like. And then we've developed what I believe is the first geodynamic model of plate tectonics that could be used in middle school, which is an interactive dynamic plate tectonic model of an Earth-like planet. And that's important to understand. It's Earth-like. I'm not modeling the evolution of Earth here. So GEODE Technology, the framework, and this is probably all of Concord Consortium's modeling basis, which is you need to have students interacting and experimenting, and once they're looking at it, then they can start hypothesizing and developing their own understanding. By having a dynamic model, you also can get into causal mechanisms. And students can observe emergent phenomenon either through the dynamic or even through the data modeling, and then apply that to real world. It's one thing to have it separate, but it's also really important to remember that we have to make this make sense, and so applying it to the real world. So I'm going to show you the Seismic Explorer. This is our data model set, so let's see if I can do this effectively.
Do you need to be connected to the internet?
I believe I am connected because I am hardwired.
Got it.
So here, let's see. So this is what a student would look like. I tried it earlier, so that's why I was all right. It's a map, and what we provide for students in the map is various ways to view the Earth. So you have here, this is a satellite view. We have a relief map, and so you can see where landforms are distributed around Earth. And we also have a street map. And why a street map is because geography is not the strongest suit for middle school and high school kids. So you say, okay, let's find, the East African rise, where would I go? That kind of thing. Or, let's look at what's happening in Japan. We want them to be able to find it. So that's an important piece. The other thing that we include are plate names, so that when they're answering questions, they can talk about it. Plate boundaries, continent and ocean names. And then we have earthquakes and volcanoes and plate motion. And so, I personally like the satellite view myself. Students then, get to play and see earthquakes. Here it's 1980 until today. It brings in data every single day from the U.S. Geological Survey. And they can see that, there's a lot going on Earth, right? But what you can also see very quickly is it's not evenly distributed. There are patterns. And the yellow and blue is not everywhere. And, we have for the key, we can show, that the different sizes, right? You have the different size magnitude, and you have the different sizes, and the different colors or depth. So we're seeing, yellow and blue are deeper than the red. So what's going on? The other thing students can do is they have the option of only looking at super big ones. Where are those? Or they can also look for a specific time period, right? So I only want to see what's happened in the last, bit of time. So they get to experiment with that. I will tell you, kids have zero trouble figuring this out. But what is interesting is what's going on, right? What are we seeing here? And so we've given them the option to draw a cross-section, right? So you just click on this and let's draw a cross-section here. So this is where visualizations become very important, and how do you help kids make sense of this, right? So what you see is a really beautiful pattern, right? So a kid has no idea what is going on here. This is the inquiry. Let's try to figure this stuff out. Their orientation, you still have the map view from the top, and you can rotate only about 90 degrees, and this is because kids can get disoriented. So we have limited that. But, and the other thing is, my experience of kids drawing cross sections, they tend to draw it along as opposed to perpendicular to. And so thus we have it this cube, so that if they do that and they rotate, they'll see this pattern either way. But you can imagine if you look at this and then you go someplace else on Earth, and let's draw a cross section over here. Whoops, I didn't come back. It doesn't go down, right? So you start to have them make sense out of, what's happening in one place on Earth versus what's happening in another place on Earth. So this model is data. The other piece that I will show you, I'll go back, is you add in volcanoes, and you see volcanoes are not actually distributed everywhere either. And if, stop. I don't want to be doing that. Cancel. Okay, there. This always happens when I demonstrate. It's like I'm trying to show too many things. So one of the patterns that we have kids look at is an example of, if you look over here where the volcanoes are, they tend to only be over the yellow, right? So what we know the science is that at about 150 kilometers down is when you actually have the heat enough to get the waters and the stuff to melt at the surface of the subducting plate. And that's always about where the volcanoes are. So it gets students to start looking at those kinds of patterns. And then, we also have the option, and I'll show you in the curriculum, to only reveal as many data sets as we want kids to explore at a time. But then we can also put plate movement. And so the arrows show the rate of motion. So here it's 23 millimeters per year, spreading, right? And so the kids can get information about that. So all of this data, and you can hide data. You don't have to show everything at the same time. If you just want to see the plate boundary types, the different colors. And again, we show kids all about the keys, right? So helping kids make sense of it. All right, so let me go back to my talk. So that was one model. Any questions about this model?
I really like the visualization. Just a couple. Can you put the volcanoes on the cross section?
The volcanoes are only on the surface of the cross section. So we're not showing. We're showing different time periods also. So we're not showing eruption as it plays either. They all just sort of come on because it's thousands of years as opposed to decades.
And then can you compare two different cross sections in one experiment?
No, but in our curriculum you can take snapshots
Okay.
and compare snapshots, and I'll show you that.
Do students ever ask about the source of the data? For example, how do we know about all those earthquakes under the ocean if no one lives there?
Sometimes they do, and I think in our curriculum we scaffold sort of where does this data come from, and so we talk about that. There's what the USGS is doing within their curriculum.
How far back in time do you go?
In terms of earthquakes?
In terms
So the
of model plate motions.
right. So we in this model, right? So we have earthquakes that we can go back to 1906, but it's a lot spottier in terms of how because it's only the big earthquakes that they have recorded. We tend to do 1980 to the present in terms of earthquakes and thousands of years for volcanoes. And then the data with regard to the plate motion is based on current GPS data. So, we've got different data sets. We've got the GPS data from UNESCO. We've got so we pulled in data sets and represent them
The students don't ask about deep time?
Not yet. In the next model they do, and I'll show you why in a second. Because deep time is an issue, and so how we try to address that. Let me just, I'm going to be going back and forth just because that was the best way to do this. So this is our second model. This is the Tectonic Explorer. So this one is based on this is dynamic, and it's based on physics principles. So it's a bunch of hexagons wrapped around a sphere, if you will, and then there are forces are applied to each sphere, and physics engine calculates the forces, the torques, angular acceleration, angular velocity, mass, inertia. Additionally, each one of these hexagons, and it's hard to see, but you can see it's very oddly shaped and colored, but it's because each hexagon has information about what kind of plate it is, the elevation, and what's happening below the surface. There's a lot happening in each one of these little hexagons as it's interacting. So, back to the models. So I'm going to demonstrate how students interact with our Tectonic Explorer. So it's Earth-like. The idea is it's Earth-like. It's not Earth. But the interactions are based on our understanding of plate interactions on Earth. In order to reduce the cognitive load, we have the opportunity to have students look at different configurations of this planet. You can start them off simply with 2 plates or 3 plates, and then see what happens. So I'll do a 3-plate one. Students are when you just put the model, students play, right? And I'll talk about scaffolding. But what you can do here is you can draw continents. You can, add continents anywhere you want. You can rotate. I'm not rotating. You can. So you can draw a continent across the plate boundary. You can erase a continent if you don't like it. The next thing that students can do is they can assign forces to plates, and this basically gets the plates moving in a certain direction. Randomly assigning, right? The next piece that they do, and we have to get them thinking about it, is assign plate density, because ocean-ocean interactions, one of them has to be denser than the other for it to subduct. And in order for what our ultimate goal is, can you set up this tectonic model to in some way reflect similar things that might have caused something on Earth? And so, you know, understanding if the green plate is denser than the pink plate, it will go down. And what you can see is the lighter color is where the continents are. And then you finish and things start to move, right? So what you're seeing is on the continent above, there's some sort of mountain building going on. You have some divergence going on below. And, you know, deep time, we start to calculate how many millions of years, right? So we see that we put on this model based on what we know about time it takes for oceans to open up and the time it takes for mountains to fill. We do an approximation. So we start to put in time there. We also have the ability to draw the cross-section. So the cross-section is now what's happening below the surface. This too is rotatable, so in case they draw the cross-section in the wrong direction, we do put videos on how to draw cross-section. And when you play, it is also going to move, and it's dynamic also. So they're seeing change over time with this model. It's magma. Magma, but that's where volcanoes are forming, right? So if you imagine, you know, what's happening in South America, right? You have something subducting and you have volcanoes along there. So
And what's in the engine that triggers that?
what is in the engine? So the depth at which the subducting plate, so this plate down here, that's about 150 kilometers in our model estimation, about, give or take. The other thing you can start to see also is that there is a little bit of a trench that's formed here. You can see the different kinds of crusts are represented. So we're trying to get at, you know, it's close to Earth, right? You know, you can see how this might work. And, you know, the students can see what's happening on the other side of the Earth. So we have subducting on one side. What if we draw the cross-section here, and the students can see that, oh, it's diverging, right? And when you play, you'll see that it's, you know, there is the essence of things are happening there. We try to use the same sort of topographic coloring, so the maps are somewhat familiar. What you also see are, over here, island arcs are forming. Whoops. So the students can stop and start and restart and change their setups and experiment and come up with sort of what's happening, what are the interactions. Any questions? Yeah.
How do you structure the student interaction with the model?
You're leading right into the next part of my talk.
I'm so glad I could be a shill.
Exactly. So let's go to the next part of my talk. Unless somebody else has a question before I go away from the models.
So, in the model, is it like predetermined, or is there any randomness? Like you're destined to form island or there, or there are like chances of island.
Right. So the way it is designed that if you have two plates moving towards each other and one is subducting, and the hexagon that has subducted hits a certain depth, then you get an island forming, right? So it's random in, how have the kids set up the forces and what's the angle at which that plate is going down based on that. But once it hits a certain depth, that's where the island arcs. So you will never get island arcs forming all the way through. It'll always be within that sort of band near the plate boundary. So there's nothing, the predetermined is there's things that are in the program that are if-thens, if this plate is subducted and the hexagons are where all this information, or if you have continents colliding, what happens in the force. Here, I can show you, I can keep going with this, but what we do know, right, when you get Pangea, right, when all the continents come together, at some point it breaks up again, right? So there's forces that going, and then there's what's happening in the Earth that all of a sudden things break apart. We also know that oceans are never more than about 220 million years old. So, we have that starting to break and subduct so that you end up closing up. So lots of things are happening that are calculated if you allow it to run over a longer period of time. I thought I saw another question. Yes?
Are the calculations all done on a server at Concord Consortium or?
It's, yes, because, yes, it is all done. Because this is all web-based and web-delivered. Yes.
And at some point, does it hit like a load threshold where too many students doing calculations at the same time?
We haven't yet seen it. It does slow down. We, of course, work on super fast Wi-Fi, and you bring it into class. It's like, wow, it does take millions of years for this to happen. It does slow down, but it doesn't, grind to a halt kind of thing. We constantly are trying to optimize it so that it runs faster, and it works on tablets and on Chromebooks quite well. So, that's always our goal. It is one of our slower models because there's a lot calculated. All right, so getting back to, okay, I'm keeping an eye on time too. Play. So, what the question that led to this one is, these models without scaffolding, kids have no trouble. They have no trouble interacting with it and making the cross-section like, woohoo, and spinning the Earth and trying to make Pangea. They have no idea what's going on, and the cognitive load, both of the data and this model, and then I'm trying to get them to put it together is hard. Yeah?
You talk about a lot of terminology that one learns about in physics.
Right.
So do you assume that knowledge, or do you teach them the physics they need?
So I assume no knowledge, right? So these are middle school kids who've never ever thought about this stuff before. So when we scaffold learning with this, we, at the appropriate points, bring in the necessary information. So, that model is sort of the sophisticated model, everything you can do. And we limit as we, let's focus in, let's try to make sense out of, we introduce things slowly with the kids. So the way we work at the Concord Consortium is you come up with like the most sophisticated master model, and then what we do is we bring kids in or go to schools and do focus groups with them to understand where the problems are, where they have trouble making sense out of it, where they have trouble manipulating it as we develop the features. And then we design an online curriculum that we then help the teachers use. So it's a this is 2 years of process of trying different features of the model with kids, with adults even, and then figure out how to introduce the content that goes around it.
Where do you get the kids to try it out?
Oh, we go to school. We try to go to schools with good diversity. So I typically test in Framingham. We've gone to Lowell. We do it in Natick. You know, occasionally, you know, we'll use our own kids. You know, if we need just need to test this really quick thing, you know, then
Going to Boston.
you know, it's not as convenient. I mean, it's harder. We have in the past, just in this particular case, we haven't gone to Boston.
We have a very complex IRB process.
Yeah.
Sorry?
We have a very complex IRB process that we have to go through to do research.
Yeah. All right. So, what we do know is if you just put the models in front of the kids, they're not going to learn what you think they're going to learn. If you just put it in front of adults, they're not going to learn what you think they're going to learn. What I've seen is them drawing cross sections across the entire map in Seismic Explorer. So all of a sudden, you just have a pretty rainbow, but it's not showing you any features. Or so what we do is we scaffold a online learning curriculum, and we frame it with a question. This one is, what will Earth look like in 500 million years? We don't think the kids are going to answer that question accurately. Nobody can. But based on going through 5 activities, and these activities will probably last, well, when we did it in the spring, last about 8 class periods without other instruction. So, you know, other things going along. Students start to get the information that they can to start to speculate, right? You know, like, oh, if we know the plate motion going about so many millimeters, and then you can, okay, if you add that up over a lot of time, where might X end up being? Or, you know, so they can start to think about it. And they've seen, and they will see, paleo maps. What did Earth look like in the past 500 million years? And then each activity, we try to use real-world cases, right? So can you think about what's happening at the Himalayas or in the mid-ocean ridges? And then we scaffold them to, you know, here's a place on Earth. You know, we'll show you pretty pictures. Then, you know, think about real-world, what's going on at the real world. They have to explore relevant data. Some of that data is from the Seismic Explorer, and some of it is other data, GPS data, topography. They then create a model hypothesizing about what's happening to create that, and then they have to write a scientific argument. And getting at the vocabulary, we don't introduce the words plate initially or convergent boundary. We want them talking like plate 1 is moving towards plate 2 and is going underneath, and because we want them to get the idea first, and then we get into the vocabulary. Because transform boundary in particular, that one means nothing to kids, like that word, like nothing. So the vocabulary comes in later on in our curriculum. And then getting at the 4-part argumentation item sets. And this is going to get back to what I was talking about earlier in terms of limitations. So my partner for the last few projects have designed this 4-part item set based on claim evidence reasoning that a lot of the world is out there. But we pay specific attention to certainty as the qualifier and as the reasoning part. So what we have students do in argumentation is they have to put a stake, make a claim. This is what I think is happening. And then they have to explain based on the models or the data why. And then we ask them to rate on a Likert scale from 1 uncertain to 5 very certain. How certain are you that your evidence and claim are reasonable? And add to that, we ask them to do a rationale for their certainty rating. So, you know, blow the kid's mind. What do you mean an uncertainty rating? And what we find is that sort of reasoning, oh, you know, this isn't Earth. the model isn't Earth, it's a limit. They had to it's not exactly like the Himalayas. It doesn't look as tall as I thought it would be, whatever. Or, is there other data sets I need to be looking at? So getting the kids to think, and they start with, I don't know, what do I know? It's new to me, right? And we try to help them and scaffold them through the curriculum to look at the science and the models and think about the limitations. And then to even think beyond, what do scientists actually know, right? Some things they're certain of and some things they're actually still researching. So, there is a progression. And we've been doing this for 10 years and have a very solid rubric and construct for evaluating their uncertainty rationales. We've gotten so good that we've been able to do that through automated scoring and give them feedback on it in our previous curriculum. If we get enough answers, we'll be able to do that here. But it's solid enough that we can tell from the kinds of words they're putting together, they're in the personal, there's a duality, like, I don't know, somebody told me, I'm not sure, to, we're talking about the model, to we're talking about the greater science, right? And so we can help them move through automated feedback. We have that construct. It's online if you ever want to see it, and we have done it successfully with automated scoring.
So for a teacher who's not at Concord Consortium, how much preparation and training do they need to deliver the curriculum effectively?
Effectively, that's a good question. Right, so anybody, well, we haven't yet put this curriculum on, my prior curriculum has said has been in all 50 states, and I've only worked with a handful of teachers. You can pick it up and use it. The effectiveness, we're still working on in terms of what kind of teacher support would make it more effective. I think that it's pretty well scaffolded that you're not going to get dumber using it if the kids are going to be able to learn. But, they're really thinking about the systems and the system dynamic stuff. A lot of earth science teachers aren't trained in earth science, and so they require, I think, just more attention to how do you think like the scientists, what are we presenting in the systems dynamic way.
So there's a teacher's guide that sort of accompanies this to give them that.
Yes, so we have a teacher guide, and we're now working on a dynamic teacher interactive so that as they go through our curriculum, they'll have a teacher view that things will pop up like, here's some background, or this is what you should look for in the model, So we're working on trying to have something for them like at point of use. All right, so I'm going to show you the Andes as is done in our curriculum, just so that you can see what a page in an activity might look like. And so, we have to orient them. Kids in the United States don't necessarily know where the Andes are. So we focus in, here's a picture. This is the Andes. And then we explain to them what they're going to do for this case is that they're going to collect elevation data. They're going to look at, what this dark blue is all the way to the brown and white. They're going to look at earthquake and volcano information. They're going to set up a model, the Tectonic Explorer, and then they're going to develop a scientific argument. So this is sort of working through. Now I'll tell you, this is version 2 of our design study. We're already up to version 3 we're working on right now to even open it up a little bit more to more inquiry. But we start with, what do you think? How do you think it formed? They don't know anything, right? They haven't seen things moving together, moving apart. This is the first case they've come up to. But let's get them to just put a stake in the ground. They'll come back to it. And then we show them this profile here so that they can start to see, wow, it gets really deep over here. And then it gets pretty tall.
What does the line represent?
That's elevation. Right, so it's the surface. This is 0 is sea level. So this is below sea level, going way down, and then going.
It's below sea level.
I
know, but
So we're.
we don't have places in South America that are 8,000 meters below sea level.
Off the coast you do.
Off the coast you do. right? So over here, you're working your way, and yes. You're working your way from point A to point B, and there is a little video to explain this profile. Yep. Okay. And then we, try to scaffold their visualization, and we have check answers, right? So that this is not a trick. We want to make sure that they're making sense of the visualization. And so they can say, let's try this. Check answer, sorry, no, you kind of have to try again, look more carefully, and we give feedback. And then, we bring them to what's going on here at the Seismic Explorer, and I've already played this, which is probably a bad idea. And we scaffold them, to look at the relief, look at the landforms, and then, play the Seismic Explorer, look where the volcanoes show up. And
In
they,
this case, you have kind of a widget of the full Seismic Explorer right in the curriculum.
yeah.
You
Yes.
don't send them off to the full one.
No.
You're limiting what you want them to do.
Exactly, and you can see we don't have plate boundaries here, right? We're not yet giving them the information about plate boundary. We're just look at what's going on. So we take that big model and we can zoom in or zoom out to certain locations and turn on and off any of the features we think is important to keep away for now, or give them, so right now they don't have to find where the Andes are. We've already put it there, right? And then we also, limit the data type so that they're only looking at earthquakes and volcanoes that are happening. And through and then we try to get them to think about, what's the light blue and the dark blue in the topo map, and what are the different colors representing, and draw a cross section, over here. And then they can see, what's, oh my God, like this is an interesting colorful pattern. And we get them to take snapshots, as you were asking. You could take a snapshot of it. And the model will show up right here, and you can annotate it if you want, if it works here. There it goes. You can draw on it, and you can annotate it, and you can give yourself, notes. We can make an album where you can have multiple images. And then, we ask them to set up a model so it's somewhat like what they think is going on. And I don't, right now I already put a continent on it, but it's not looking very happy, so.
Still in the snapshot.
Oh, that's why, thank you. I always do that. Get ahead of myself. So here we assign horses. They haven't yet learned about density, right? So we will get into that momentarily. But, we give them the idea. And, well, so that is an interesting question, right? So they understand that they can draw, right? We've shown them how to do this, like put these arrows. What's it doing? And so over experimentation with it, they start to figure out, and then we actually talk about what's going on with those vectors. But yes, there's a lot going on and assumptions that we're making that we're not revealing to them when we start. We're just like, play, experiment. Can you get it to do it? And in this case, we'll see. Because, yeah, so I had the density not quite right? So the density of the ocean plate wasn't going to go down because I had the density backwards. And once you get a continent to hit a boundary, it stops. It's not going to subduct. And so they're going to like, oh, what happened? Why didn't that work? Let's try again. So there's a lot of experimentation that goes here. And then we get them to do the argumentation. And then we talk about geologic time. So, so starting to get them to focus on, the time period, this 188 million years that happen, and yet earthquakes happen in how long? And why aren't there earthquakes in the Tectonic Explorer, right? We have to have them start to think about things like that. So that's what happens in our curriculum. And I'm just about done, which is just about the right time, I think. I talked a lot more than I thought. And so here's the stuff that we're currently researching. So one is, are they learning the content? Second is, what patterns emerge from students' interactions with the models? So what are their modeling practices? And we do that by observing the students, capturing screenshots, going into classrooms and videoing, and through logging their actions and their click streams. And we can see that if kids don't create cross-sections, we can give them a pop-up and say, you can't answer that question because you haven't quite finished working with a model the way you should, or you haven't let it run long enough, or, So we're starting to figure out how to use student click streams to give feedback to students. Then look at their argumentation evidence. How are they using the evidence from the models to develop their arguments? And finally, because our partners are all about the teacher practice, they're researching how teachers are using that in classrooms. So they're observing teachers, and then also how our teacher PD works and doesn't work.
Before you leave that slide, you said evidence generated from models. What exactly do you mean by that? How do you distinguish evidence from models?
So how we distinguish evidence from models is, are they actually looking at the emergent phenomena of the model and applying that accurately, or are they looking at the data and as that cross section where it subducts in one place and does in another? That's emergent phenomena that they use as evidence when defending their claims or using for explanation. So that's the phenomena. But again, I talked also about, we asked them to think about the limitations of what the model is able to represent versus what's happening in the real world. Does that answer your question?
Not quite, but it's okay.
Okay. So just preliminary results from our first design study, that they improved on content and argumentation. We still need to figure out how to scaffold better the thinking about temporal reasoning. So we're trying new things in this current fall, and how to really invoke mantle convection as a causal mechanism. Our model is not showing that far down, so we're not showing the causal mechanism coming from mantle convection, and so how we're going to connect those things is a bigger question that we're working on more deeply. And finally, introducing uncertainty more explicitly. We do it implicitly to start with, like, just put the questions out and see what happens, because they're curious where kids go with it. It's excuse me. It's how we determine, on the whole, whether or not kids are improving significantly or not. So it's a statistical analysis of student work.
Change in units of standard deviation. Change in units of standard deviation.
It's basically the gain.
It's a gain, right?
It's
the effect, right?
In standard deviation.
Yep.
So it sounds kind of like you're overloading the word model, because you have your simulation, which you're calling a model, and that generates emergent phenomena for the students, who then create like a theoretical model of how the Earth works.
Right.
But you're calling that a model, like.
Yes.
Do you say that all to the students as well, that like using this model make a model?
We don't. We do ask. How explicit are we? So we do talk about, here you're going to use this model to try to create a phenomenon. So we're using this as a model. We're not necessarily connecting it to yet, although we're working on, that Tectonic Explorer is the theoretical model for the data that you've been observing in Seismic Explorer, right? So can you connect those? So we are now getting more explicit about that. In our first iteration, we were not that explicit.
Okay. So there's a theoretical model generated by scientists
Right.
that the simulation rests on,
Right.
and then they're using that to build their own model.
Right.
And like making that explicit. Okay.
We're trying. We're getting there.
Okay.
Yeah?
Can you say more about how you assess their argumentation improvement? So I know you said that you have some standardized coding and a rubric, but could you give an example of what's like a weak argumentation and what's like a stronger explanation or rationale that they would give by the end of the
Right. So we evaluate each part of that argument independently and then put the argumentation together. So the claim, is we have a rubric for the claim, and then we have a rubric for the explanation, and then we have a rubric for the uncertainty attribution. And so each of those are scored individually. And so, if you start with, because I saw it in the model, that's not very good evidence, right? You saw it, at least you're referring to the model, as opposed to just because I said, or because I'm smart, right? And then similarly with the uncertainty rationale, a weak uncertainty rationale is I'm certain because I saw it, right? So what? What are you certain about in terms of the evidence, and a more sophisticated reasoning would be, I'm moderately certain because the data shows that the earthquakes are happening, along this boundary, and then the model is showing that the interactions of the plates make sense because, so you can see that they're adding together. A very sophisticated argument would say, this model isn't really Earth, right? There are limitations to what was put into that model, or, I don't know, the model's mountains weren't as high as the Himalayas. Like, what's going on there? Whatever. I mean, they start to think about that, or they start to think about, I only have a limited data set. Is there more information I might need? So that's sort of the progression. Is like, I'm certain because I did a great job of the model. I'm so smart. That's actually low score. Yeah. And we can give them feedback, and with the automated feedback, we catch it right then. Like, it's within seconds. We say, you actually need to give us some evidence from the data, the model, from what you're talking about.
And so the middle school students get to those really sophisticated recognitions that...
Yeah, well, especially when you give them feedback, right? When you start off, depending on the teacher support, right? We also give teachers, students answers in real time so they can see. And so multiple choice are scored immediately, open-ended ones. When we get enough, we'll be able to do automated scoring. But they can see in real time, how fast they're progressing through this online module. Oh my God, none of these kids understood that point A was in the ocean, and we need to, hey kids, come up here. So they're seeing student progression and student answers with a teacher dashboard in real time. And a lot of them have tablets that they will carry around with them to help them manage what's going on in the classroom. And then, we also spend some time in our teacher PD talking about how do you deal with getting students to think about uncertainty without, especially the honors kids who have the hardest time because they're open-ended and there's no right and wrong. There's things that you need to include, but you could come up with possibly different conclusions based on the evidence that you're looking at. So, and the honors kids are, get the most frustrated with it.
How have you worked with teachers to integrate it into their existing curriculum? I can see they already have a section, or when they learn about something else geoscience related.
So, right. So the people who are adopted for at least the field testing are aware. Like, okay, when you do plate tectonics, this needs to be inserted, right? You may have your favorite lab. Have the kids playing with food to show plate tectonics, whatever. But we need the kids to work through it. What we try to do actually is try to get this curriculum early. Most of the time, plate tectonics is taught at the end of geology. Rock cycles and everything you need. Okay, now learn about all the volcanoes. Now learn about earthquakes. And then, oh, by the way, it's all pulled together with plate tectonics. And we're trying to flip that so that the plate tectonics is sort of, it's like DNA in biology. Like if you understand this, then everything else fits in. And one of the things we're going to be adding into the Tectonic Explorer is rock types, right? So what's the ocean floor? What are continents? Where do you find sediments? Starting to get that rock cycle thing in there also a little bit. It's not every kind of rock, but at least start to think about it. But the teachers will always, in earth science, teach plate tectonics. It's sort of core. They probably won't spend as much time. So that's where you have to kind of, it's okay. If you spend this time, then the volcanoes will be easier and the earthquakes will be easier, that unit. So it's part of their curriculum, so it's not, additional.
Okay, so then do you see this model expanding into more geoscience so it becomes like a full earth science curriculum?
That's my goal. I want to take over earth science. Yes. Yes, I do see it expanding and this being sort of a foundation and, then getting into stratigraphy and understanding that and getting into rock cycle. And so I can see that happening for sure. But yes, it is my goal to take over earth science.
Is there a way for kids after they're done with this? It looks like things are scaffolded pretty much into the activities, the pieces. Is there a chance at the end that if they have their own questions, like, there's this thing, the volcano in Iceland's probably going to go pretty soon, so I want to see what happens in Iceland. Can they go on their own, or what happened? How did that Hawaii? When there's something going on in Hawaii, can they do something on their own too?
So we put these models on our website as standalones, right? So anybody could go and use and explore. And in fact, when Hawaii eruption happened, all of a sudden people were like, wait, what's going on?
Right,
what about the earthquakes? And and I didn't understand the earthquake. So they went right to the Seismic Explorer, and we actually made a little video and put it on Twitter and Facebook and whatever else you do now in social media. But yes, so the opportunity is that these models will also stand alone for exploration. The scaffolding is, really to march them through the learning, but it's there. And teachers can take a model and show whatever they want. Any other questions?
I actually just wanted to comment. I wanted to go back to Jackie's question and Erwin's comment that this work, which is absolutely wonderful, is really part of a whole class of projects that where your students are looking at the data first. They're looking at data without ever having gone out into the field necessarily and studied geological landforms. And that's similar to things like Ruth Crum-Hansel's project at EDC, Oceans of Data, where you're looking at fish migration and shark migration, so forth, or our own spectroscopy project, where you're working with NASA's spectra of planets, and you've never been to them, and you don't know what a spectrum is. So, and so this class of projects is about is starting with data and learning how to use data and models in the same way that you might have gone back when you were a kid and worked with prisms to understand light and color and just see how things work. Here you're starting with the data, and one reason why I think this project is so important is because it's really the future of where a lot of classroom learning is going, because we're living in the age of big data. We have these amazing data sets that we didn't have before. And I just want to make that explicit, because I know there's a lot of, we're all coming from a previous model in which first you work with the real stuff and then you abstract physical principles from it. Here, the geo model is a black box model in a way, because you don't have to know about vectors, you don't have to know about the physical forces and drag and so forth, but you're seeing how it works, and you can then you can then use, as you're saying, use that as the primary reference. When you do go out into the real world and you're on vacation, you say, oh, wait a second, remember that.
Yeah.
So it's not necessary to go to first principles or start in the field.
Right.
And that's sort of a, if you like, it's a hypothesis that underlies, well, it's an assumption that underlies this kind of work. And it's great to see that it's working so well.
We are very late for lunch, so if everybody can go grab your pizza salad, then we can keep our discussion until 12:15. So that's another like